It was Jacob Lew, U.S. Secretary of Treasury from 2013 to 2016, who said, "A budget is not a calculation of numbers, but an expression of our value and aspirations." In this lesson, we're going to determine the dimension of a matrix. We're going to add, subtract, and multiply matrices. And we're going to multiply a matrix by a scalar. All to be able to answer the question, how else can budget data be organized? First, let's make sure we're ready for this lesson by taking a look at warm-up number 2, which is to graph the line represented by the equation y is equal to -3 plus 2x. So to do this, we bring up some graph paper. Now we see that the y-intercept is at -3, so we move down 3 and place our point. The slope is a +2, which means from that point to move up 2 and to the right 1. Given these 2 points, we now have our line. Also, we're going to find the slope and y-intercept of 70 is equal to -2y plus 8x. Well, if 70 is equal to -2y plus 8x, then 2y plus 70 is equal to 8x. 2y would be equal to 8x minus 70, and y would be equal to 4x minus 35, meaning the slope of this line is 4 and the y-intercept is -35. Now, let's take a look at a problem you will be able to do at the end of this lesson. As listed in their budget chart, Enrique and Sofia have secondary income from online sales of customized cookies, cakes, and cupcakes. They want to determine the monthly income from sales based on the data they have collected at the end of the year as shown in these two charts. We are going to set up a number purchased matrix and a price per item matrix. We're going to use matrix multiplication to determine the income from each item by month. And Enrique and Sofia only want to enter their profit they made from the sales of each item into their income budget chart. They make 40% profit on the cookies, 20% on the cakes, 30% on the cupcakes. Set up a percent profit matrix and multiply the matrix times the income matrix determined in part B. Be sure that the percent matrix has the correct dimensions for the multiplication. Let matrix N be the number purchased matrix. Let matrix P be the price per item matrix. So first we need to figure out if we can multiply these, and we can see that this is a 3 by 1 and this is a 1 by 3. So we can see that this is a 3 by 3 and that this is a 3 by 1. This means that we are going to wind up with a 3 by 1 as our answer. So 65 times 3 plus 40 times 3 plus 75 times 3. This is going to give us our first answer. Then we will have an 80 times 30 plus a 70 times 30 plus a 150 times 30. Then we will have 120 times 5 plus 200 times 5 plus 300 times 5. So 65 times 3 plus 40 times 3 plus 75 times 3 is 1770. 60 times 30 plus 70 times 30 plus 150 times 30 is 3090. 120 times 5 plus 200 times 5 plus 300 times 5 is 7,800. The income for sales is 1770 in October, 3,090 in November, and 7,800 in December. We're going to let I represent the income matrix we just determined in Part B. Since I is a 3 by 1 matrix, it is important to set up the percentage matrix in a way that will allow the multiplication to be defined. There's only 2 options to do this. The percentage matrix can be a 3 by 1 or a 1 by 3 matrix. Let Z represent the percentage matrix. So we have 2 things to take a look at. X sub 1 times I. Now X sub 1 is a 1 by 3 matrix. where I is a 3 by 1 matrix. So if we multiplied this, we would wind up with a 1 by 1 matrix, where x sub 2 times I, x sub 2 is a 3 by 1, and I is a 3 by 1. We can't multiply this, so it would not work, meaning we have to do this x sub 1 version times I. So when we set this up so that x sub 1 times I, we have 0.4, 0.2, 0.3. This is going to give us 0.4 times 1700 plus 0.2 times 3090 plus 0.3 times 7800. This means that we will wind up with 3,684. 3,684 is the total amount of profit made from the sale of the bakery items during October, November, and December. Sometimes consumers are hit with so much financial data that it is overwhelming. One of the keys to making sense of numerical information is organization. An array is an ordered arrangement. An array is not always numerical, but it is in this section. Only numerical arrays are addressed. Numerical arrays can take a variety of shapes. Let's look at these examples. The clock face depicts a circular array of numbers. Pascal's triangle depicts a triangular array of numbers. The Sudoku game board depicts a rectangular array of numbers. The numbers in each array shown here are organized in a particular way to make their interrelationship and meaning clearer to the reader. You have already used many arrays throughout this entire class. Anytime you are presented with numerical data in a list, a chart, or a spreadsheet, you are using a rectangular array. In this lesson, you will learn to use rectangular arrays other than budget charts to aid in your budgeting. Examine this portion of Enrique and Sofia's budget for the income they received during the first 3 months of the year. Their budget chart can be converted into a special type of rectangular array known as a matrix. A budget matrix is a rectangular array of budget entries. To build a budget matrix using the budget chart above, remove the column and the row labels. This will result in 3-month income budget matrix for Enrique and Sofia. Rather than keeping the data in chart form, arrange it in matrix form as shown. Notice that the brackets are placed around the rectangular area of the numbers to indicate that this is a matrix. Matrices, plural of matrix, are usually named by capital letters such as A, B, or C. A matrix is defined by its number of rows horizontal and its number of columns vertical. These are called the matrix dimensions. Now we're going to determine the dimensions of a matrix. The matrix shown is a 4 by 3. Read 4 by 3. It has 4 rows horizontal, 3 columns vertical. Generally, if a matrix has m rows and n columns, it is said to be m by n matrix. Each number in the matrix is called an entry or element. The position of an element in the matrix A shown is very important since each number reflects a different category or month and type of income. Elements are identified by rows and column. For instance, 350 is the third row, first column of matrix A. The entry is identified as A3, 1. A matrix can contain a single element, such as a matrix would have a dimension 1 by 1, since it has 1 row and 1 column. A matrix can contain all zeros as elements. Such a matrix is known as a zero matrix. And here is an example of zero matrix in different dimensions. A is a 2 by 1 zero matrix, B is a 2 by 2 zero matrix, and C is a 3 by 2 zero matrix. In the next examples, you will use matrices to work with Enrique's and Sofia's budget. Using Enrique and Sofia's income budget chart as the budget matrix A, where A is the matrix that you can see on the screen, identify the income budget category for each of the following elements: A22, A13, and A41. A22 is the element in the second row, second column. The $5,000 entered. The $5,000 entered there represents Sofia's February income. The A13 is the element of the first row, third column. The $3,500 entry there represents Enrique's March income. The element 4-1 is the element of the fourth row, first column. The $1,200 entry there represents January rent from the tenant. Let's check your understanding and suppose that Enrique and Sofia's income budget chart and matrix has started with the column labeled December and still has entries for January through March. If the new income budget matrix labeled B, what are the dimensions of B? Identify the income budget category for each of the following elements: B22, B13, and B44. B is a 4x4 matrix. B22 is Sophia's primary income for January, because remember, this first column was December. B13 is Enrique's primary income for February. And B44 was the March rent from the tenant. Mathematical operations such as addition and subtraction can be performed with matrices. Usually, a graphing calculator or spreadsheet software is used in order to add or subtract two matrices. In order to add or subtract two matrices, they must have the same dimensions. To find the sum or difference, you add the matrices or corresponding elements. The corresponding elements are entries in the same location of each matrix. You will learn how to combine matrices in the next examples. Now let's add, subtract, and multiply matrices. Enrique and Sofia keep individual expense budget charts for major categories in their budget titled Work-Related Expenses. Examine these charts below. Set up matrix E, which represents Enrique's work-related expenses for 3 months of the year, and matrix S for Sofia's work-related expenses for the same period. Determine matrix J, whose entries their combined work-related expenses. Here we have Enrique's matrix, and here we have Sofia's matrix. Matrix J will be equal to the E matrix plus the S matrix. To do this, we simply do the E matrix plus the S matrix. Now, 478 plus 220 will be 698. And because I know all three of these hold, I'm going to put that 698 at the top of each one. Of course, we only can add these because both matrices are of the same dimension. Now, 30 plus 10 is going to give 40. 50 plus 10 will give 60. And 30 with 10, another 40. 80 plus 120 will give 200. 50 and 120 will give 170. And again, 50 and 120 will give 170. 30 and 40 will give 70. And we will have that 70 in each of these three positions. And this is now our J matrix. Enrique and Sofia can enter the element of matrix J into their joint budget chart. Let's check your understanding of this and see if the commutative property of addition holds for matrix addition. That is, given the matrix E plus S, is that the same as S plus E? Well, since the position doesn't matter if it's 478 plus 220 or 220 plus 478, the J matrix would give 698. 220 plus 478 will still give 698. 220 plus 478, another 698. And if we keep adding the right side to the left side, we can see that we are coming up with the same matrix that we had in the last example. The order that you add doesn't matter as long as you do your addition correctly. So yes, the matrix addition is commutative. Now let's multiply a matrix by a scalar. Sophia will be doing a great deal of work-related travel around the country during the month of April, May, and June. She estimates her work-related expenses will be 3 times what they are for the first 3 months of the year. Determine Sophia's work-related expense budget matrix for April, May, and June. So if her work-related budget will be 3 times her old budget, then her work-related budget will be 3 times the matrix that we've previously had. Multiplying 3 times each entry, so 3 times 220 will give us 660. This holds true in all of those positions because they're all 220. 3 times 10 is 30, and 3 times 120 is 360, and 3 times 30 is 90. Each of the entries of Sophia's work-related expenses matrix will need to be multiplied by 3 in order to get her new expenses. To multiply a matrix by a real number, multiply each of the elements of the matrix by the real number. The real number is known as the scalar, this operation called scalar multiplication. Let W represent Sophia's work-related expense budget matrix for April, May, June, then W is equal to 3S. Let's check your understanding. Sophia's employer will reimburse her 80% of all work-related expenses for the months April, May, and June. Let matrix B represent the matrix of the expenses covered by Sophia's employer to determine matrix B. So matrix B would be equal to 0.8 of matrix W. So B 0.8 times that matrix W. 80% of 660 is 528. Now this 528 will hold in all 3 because it hasn't changed. 80% of 30 is 24. 80% of 360 is 288. And 80% of 90 is 72. And let's extend your understanding of this by letting matrix C represent the amount that Sophia will have to pay out of pocket for work-related expenses for April, May, and June. C can be represented by the matrix subtraction of C is equal to W minus B, while scalar multiplication that C is equal to 0.2W. Determine matrix C both ways and show they yield the same result. So up first, we'll be multiplying by the scalar 0.2. 0.2 times 660. 0.2 times 660 is 132. 0.2 times 660 is 132, and it is still 132 the third time. 0.2 times 30 is 6, still 6, and still 6. 0.2 times 360 is 72 in all 3 positions, and 0.2 times 90 is 18, which holds in all 3 positions. So now we have an answer for multiplying by a scalar. What happens when we do matrix subtraction? 660 minus 528 is 132, which will occur all 3 times. 30 minus 24 is 6. 360 minus 288 is 72. And 90 minus 72 is 18, which shows that if you multiply by a scalar or you did the subtraction, you get the same answer. Let's take a look at some matrix multiplication. Unlike real number multiplication, where any 2 numbers can be multiplied together and the order of the multiplication does not matter, matrix multiplication can be more complex. In the previous example, you learned how a matrix could be multiplied by a real number. The dimension of the matrix did not matter. For matrix multiplication to work, the most important thing to remember is the 2 matrices can be multiplied together if and only if the number in columns of the first matrix is equal to the number of rows in the second matrix. If that condition is met, the product of the 2 matrices will have the same number of rows as the first matrix and the same number of columns as the second matrix. In general, if matrix A has a dimension m by n and B has dimension n by p, the product of the 2 matrices will be m by p. Before attempting to multiply any 2 matrices, you must verify whether or not the 2 matrices meet the condition described. If they do, you should then determine what the dimension of the product matrix will be. Examine these samples in which the values of the matrix have been removed so you can focus on the dimensions of the matrix. Let matrix A be equal to this box and matrix B be equal to a box. Now A is a 1 by 1 matrix and B is a 1 by 1 matrix. These 2 inner numbers being the same mean my matrix A times B will be a 1 by 1 matrix. If I multiplied matrix A, which is a single box, by matrix C, which is 3 boxes. A is a 1 by 1 matrix, where C is a 3 by 1 matrix. And you see 1 and 3, they're not the same. This cannot be multiplied. If I were to try and multiply matrix E and matrix F, matrix E is a 4 by 1 matrix, where matrix F is a 1 by 4 matrix. Seeing these two ones lets me know that this can be multiplied, and I will end up with a 4 by 4 matrix. If I were to try and multiply matrix G and matrix H, I can see that matrix G is a 2 by 3 matrix, and that matrix H is a 3 by 3 matrix. These two 3's being the same means they can multiply, and I will get a 2 by 3 matrix as a result. It is important to notice that unlike real number multiplication, for most matrices, matrix multiplication is not commutative. The following properties apply to matrix only when the rows and columns meet the conditions necessary for the operation. So the associative property A times B times C is also equal to A times B times C. We can also have the distributive property, which is A times B plus C is equal to A times B plus A times C. In the next examples, you will learn how to multiply two matrices in the context of a budgeting process. As listed in their budget chart, Enrique and Sofia have secondary income from online sales of customized cookies, cakes, and cupcakes. They want to determine the monthly income from sales based on the data they have collected at the end of the year, as shown in these two charts. We are going to set up a number purchased matrix and a price per item matrix. We're going to use matrix multiplication to determine the income from each item by month. And Enrique and Sofia only want to enter their profit they made from the sales of each item into their income budget chart. They make 40% profit on the cookies, 20% on the cakes, 30% on the cupcakes. Set up a percent profit matrix and multiply the matrix times the income matrix determined in part B. Be sure that the percent matrix has the correct dimensions for the multiplication. Let matrix N be the number purchased matrix. Let matrix P be the price per item matrix. So first we need to figure out if we can multiply these, and we can see that this is a 3 by 1 and this is a 1 by 3. So we can see that this is a 3 by 3 and that this is a 3 by 1. This means that we are going to wind up with a 3 by 1 as our answer. So 65 times 3 plus 40 times 3 plus 75 times 3. This is going to give us our first answer. Then we will have an 80 times 30 plus a 70 times 30 plus a 150 times 30. Then we will have 120 times 5 plus 200 times 5 plus 300 times 5. So 65 times 3 plus 40 times 3 plus 75 times 3 is 1770. 60 times 30 plus 70 times 30 plus 150 times 30 is 3090. 120 times 5 plus 200 times 5 plus 300 times 5 is 7,800. The income for sales is 1770 in October, 3,090 in November, and 7,800 in December. We're going to let I represent the income matrix we just determined in Part B. Since I is a 3 by 1 matrix, it is important to set up the percentage matrix in a way that will allow the multiplication to be defined. There's only two options to do this. The percentage matrix can be a 3 by 1 or a 1 by 3 matrix. Let Z represent the percentage matrix. So we have two things to take a look at. X sub 1 times I. Now X sub 1 is a 1 by 3 matrix. where I is a 3 by 1 matrix. So if we multiplied this, we would wind up with a 1 by 1 matrix, where x sub 2 times I, x sub 2 is a 3 by 1, and I is a 3 by 1. We can't multiply this, so it would not work, meaning we have to do this x sub 1 version times I. So when we set this up so that x sub 1 times I, we have 0.4, 0.2, 0.3. This is going to give us 0.4 times 1700 plus 0.2 times 3090 plus 0.3 times 7800. This means that we will wind up with 3,684. 3,684 is the total amount of profit made from the sale of the bakery items during October, November, and December. Let's check your understanding and set up a matrix of expense percentages to determine the total expenses for the online bakery. If they make 40% profit on cookies, then cookie expense is 60%, which means 0.6. For the 20% profit on cake, the cake expense is 80%, or 0.8. For the 30% profit on cupcakes, the cupcake expense is 70%, or 0.7. To find the product, we're going to multiply the expense matrix and the income matrix. There, the net cost of $9,036 to produce the bakery items. Let's extend your understanding further and find the product of these two matrices. First, we need to determine that they can be multiplied. This first one is a 4 by 3. The second one is a 3 by 2, meaning our end product should be a 4 by 2. To do this, we're going to say 3 times -6 plus 5 times 0 plus 2 times 9. This is going to give us our first position, and our first position will add up to be 0. Then we're going to say 1 times -6, 1 times 0, and 0 times 9 to get -6. 4 times -6, 3 times 0, and 5 times 9 are going to give us 21. 2 times -6, 4 times 0, and 6 times 9 are going to give us 42. Then what we're going to do is 3 times -5 plus 5 times 4 plus 2 times -3, and we're going to get a -1. So that we have 1 times -5, 1 times 4, and 0 times -3 to get -1. 4 times -5, 3 times 4, and 5 times -3 are going to give us a -23. And finally, 2 times -5 plus 4 times 4 plus 6 times -3 is going to give us a -12, giving us our solution matrix.